about after this talk at 2:30, lovely treats over in Vincent Hall tea room that those of you who are not graduate students who need to talk to our speaker immediately afterward, you should run over there and get those treats as fast as you can before they go away. No, there are plenty of treats, so, but please do go over there so we can have the grad students talk to our speaker. And let me just say, it's a pleasure to introduce my mathematical sister, Lauren Williams of Harvard University. And it's so nice to see her in person. And I'm anxious to hear about combinatorics of hopping particles and positivity in Markov chains. Take it away, Lauren.
So thank you so much. Thank you so much, Vic, and to all the organizers for your hard work in putting this together. My talk is meant to be totally elementary, so please interrupt if there's anything you don't understand. I'm hearing a little echo on my side, so maybe I'd better turn off my audio. Okay. How can I do this? Is it under? No. Oh. I think it's better. Okay, great. Thank you. All right. Okay, so let me start by giving an overview of the talk. I'm going to tell you about a model for particles, hopping particles, called the asymmetric simple exclusion process. And then I'm going to sort of step back a little bit and talk more generally about positivity in Markov chains, and in particular, the Markov chain tree theorem. Then I'm going to talk about variations of the ASEP and special functions. And then I'll kind of summarize and give a bunch of open problems. And I'm going to talk about work with various collaborators, and the two that I'll mention most frequently will be Sylvie Courtil and Olia Mandelstam. Okay, so what is the asymmetric simple exclusion process? So this is a very old model introduced by biologists, Macdonald, Gibbs, and Pipkin in 1968, and independently by mathematician Spitzer in 1970. And it's a model of particles hopping on a one-dimensional lattice. We have at most one particle per site. Particles can have different weights, which can affect their hopping rate. And the lattice could be a line with open boundaries, or it could be a ring. And of course, there's other choices as well. And this model has been cited as a model for traffic flow and also translation in protein synthesis. And there's been extensive work on the exclusion process. This is a very, very incomplete list of people who have worked on it. Okay, so now let me be a little bit more precise. So we're going to fix a one-dimensional lattice of n sites, each of which is either empty or occupied by a particle. And we're going to choose some parameters, q, alpha, and beta between 0 and 1. So in this model, new particles can enter the lattice from the left at a rate alpha, and particles can exit to the right at a rate beta. A particle can hop to the adjacent site to the right at rate 1 and left at rate q. And the model is asymmetric, meaning that we don't require that q equals 1. And the word exclusion means that we have at most one particle per site. And in this picture, I'm depicting particles as solid black circles and holes as empty circles. And a natural question is, what happens as time goes to infinity? What is the distribution we should expect to see? Okay, so now let me be even a little bit more formal. We're going to let B sub n be the set of all 2 to the n words of length n on letters whole and particle. So these are the different states. Then the ASEP is the Markov chain on B sub n with the following transition probabilities. So if X is a state which consists of some word in particles and wholes called A, and then a particle followed by a whole, followed by some other arbitrary string B in particles and wholes. And if Y is the same state, except in the middle, the whole and particle have swapped places, then the probability of going from X to Y is 1 over n plus 1. And the probability of going back from Y to X is Q over n plus 1. If X is a state which has a hole at the far left, and Y is the same state, but now we have a new particle which is entered from the left, then the probability of going from X to Y is alpha over n plus 1. And finally, if X is a state which has in its rightmost site a particle, and Y is the same state, but now that particle has hopped out, the probability of going from X to Y is beta over n plus 1. And in all other cases, the probability of going between two distinct states, X and Y, is 0. And the probability of staying in the same place is exactly what it has to be, namely 1 minus the sum of the probabilities that we exit. Okay, so here's a little picture of the state diagram of the ASEP when we have a lattice of 2 sites. So then there are only 4 different states. And now by sort of the fact that this is a finite irreducible Markov chain, the stationary distribution is unique. And we can compute it by solving the global balance equations, which say the following. For every state tau, we have the following: the steady state probability of being in state tau times the sum of the different probabilities of exiting that state is this sort of linear combination of the various probabilities of going towards tau, weighted by the steady state probability of being at that previous state. And these global balance equations are precisely equivalent to saying that we are solving for the left eigenvector of the transition matrix with eigenvalue 1. And both of these sums are over all states, sigma not equal to tau. Okay, so I'll just start this example so you can kind of see how this works. So let me say the probability of being at this state is A, and this is B, this is C, and this is D. Then, for example, if I look at the global balance equation associated to this state, then my equation tells me that A times the sum of the outgoing arrows, namely alpha over 3, is equal to the weighted sum of the arrows coming in. So D times beta over 3. And I could write down the other equations. Maybe I'll just write down one more. The equation associated to D would say that D times the sum of all the outgoing arrows, so beta over 3 plus Q over 3 plus alpha over 3 is equal to the weighted sum of the arrows coming in. And I see here 1/3 times B. Okay, so you can write down this system of equations and you can solve them. And that will give you the stationary distribution, also called the steady state probabilities. So if we do this for this little example, then our stationary measure looks like this. I'm putting the steady state probabilities over the same common denominator Z. And then my numerators become these simple polynomials in alpha, beta, and Q. Okay, now the sum of the probabilities is 1. So we might as well just ignore the denominators. It's like in projective space, like doesn't really matter what scaling you use. So let me just write the numerators instead. And I'm calling these unnormalized probabilities. And these are all nice polynomials in alpha, beta, and Q. So in particular, they're polynomials with positive coefficients, and they don't have too many terms. That remains true for larger n. Oh. So the natural question is there a combinatorial formula? Okay, so let me tell you. So first of all, the answer is yes. And let me explain what it looks like in this case. And to do that, I have to introduce these things called staircase tableau. So a staircase tableau, so this is part of a joint series of works with Sylvie Courtil. Staircase tableau of size n is first of all a Young diagram of staircase shape n, n-1, n-2, and so on, down to 1. I've tilted my Young diagram so that the sort of corner is down here. So we've got this Young tableau of staircase shape. And every box is either empty or contains an alpha or beta, such that no box in the top row is empty. Every box southeast of a beta and in the same diagonal as that beta is empty. And every box southwest of an alpha and in the same diagonal as that alpha is empty. So the second condition here will tell me that because of this beta at the upper left, all of these have to be empty. And then all of these have to be empty, these have to be empty, these have to be empty. And then the condition number 3 tells me that every box southwest of an alpha and in the same diagonal has to be empty. So these have to be empty, these have to be empty, these have to be empty. And so there's only 2 boxes left, which are sort of voluntarily empty. And so I'm going to refer to these empty boxes as either restricted, meaning they have to be empty, or unrestricted, meaning they don't have to be empty, but they were voluntarily empty. And we'll record the unrestricted boxes by putting Q's inside. And now we'll define the weight of a staircase tableau to be the monomial in alpha, beta, and Q that you get by just multiplying everything you see in all the boxes. So the weight of this tableau is going to be alpha to the 1, 2, 3, 4, 5, beta to the 4, and Q squared. So that's the weight. And then the type of the tableau is the word that I get by reading the letters in the top row of T and replacing every alpha by a black particle and every beta by a white particle. And so why do I make that replacement? Well, this is all related to the ASEP. And in the ASEP, alpha has to do with new particles coming in at the left, and beta has to do with particles exiting to the right, which is equivalent to holes entering. And so I think of alphas as corresponding to particles and betas as corresponding to holes. Okay, so anyway, so we get the type of T by reading the letters in the top row, replacing every alpha by a black particle and beta by a white particle. And so that's how I came up with this word here. As a small remark, there are exactly n+1 factorial staircase tableau of size n. And this is not obvious, but it's not that hard either. I can maybe leave it as an exercise to find a bijection. Okay, all right, so now how do these staircase tableaux relate to the ASEP? So the theorem is as following. Consider the ASEP with open boundaries on a lattice of n sites, and let tau be a state. Then the unnormalized steady state probability is equal to the sum of the weights of all staircase tableaux of type tau. So to go back to our little example, if I want to compute the steady state probability of state particle, then I need to draw all the tableau of type particle. And so I need to have alphas here. But now alpha forces everything to the southwest to be empty. And so this last empty box must be empty, and there's only one such tableau. If I want to compute the steady state probability of this state, then I should draw all tableaux of type particle whole. So I have to put an alpha and then a beta in the top. And now this imposes no condition whatsoever on that empty box. So it could either have an alpha or a beta or a q. Okay, so I can do that for these 4 different states. And then I can compute the unnormalized probabilities by summing up their weights. So the weight of this tableau is alpha squared, and the weight that I get from these tableaux is alpha squared beta plus alpha beta squared plus alpha beta q, and so on. And so this is how we can reconstruct the unnormalized probabilities that I showed you a moment ago. Okay. So I'll just mention that there are 2 different proofs of this result. One, you can construct a Markov chain on Tableau that projects or lumps to the ASEP. And another one uses something called the matrix ansatz due to Derrida, Evans, Hakim, and Pasquier. And actually, this theorem that I've shown you so far is actually fairly easy. But the much more difficult version is the version for the 5-parameter open boundary ASEP, where you allow particles to enter and exit on both sides. And for that, we again have an analogous result using a more general version of staircase tableau with alpha, betas, gammas, and deltas. And just to say a little bit about the combinatorics of these tableaux. So these sort of upgraded staircase tableau, if you look at how many there are of size n, there's exactly 4 to the n times n factorial. But then you can look at the generating function for this 4 to the n times n factorial tableau and look at specializations of it. And you'll get a lot of nice combinatorial numbers by doing so. So for example, if you set delta to be 0, you get a double factorial. If you set gamma and delta to be 0, you get usual factorial. If you set additionally q to be 0, you get Catalan. And you can also get Eulerian numbers, Fibonacci numbers, and so on. So we have this paper with Corteil, Stanley, and Stanton, where we looked at some of this combinatorics. Okay, so now let's just take a step back and ask, well, how unusual is it that we can write the unnormalized steady state probabilities as polynomials in the parameters with positive coefficients? Or that we can give combinatorial formulas for them. Is it always true that you can do this for any finite Markov chain? And in some sense, the answer is yes to all of these questions. And I want to explain now in what sense the answer is yes. And that goes through the Markov chain tree theorem. Okay, so what does the Markov chain tree theorem say? So let's let G be the state diagram of a finite state irreducible Markov chain whose set of states is V. And in my state diagram, so it's going to be a directed graph. The states correspond to the vertices, and every directed edge corresponds to a transition from one vertex to another. And these edges will be labeled by the probability of going from one vertex to the next. So here is a small example of a Markov chain on 5 different states. And okay, I haven't drawn self loops here. And I've chosen a sort of simple set of different transition probabilities, which are either 1 or q. And if I don't say anything about this, I'm sure I'm going to get a complaint from someone that the sum of the outgoing arrows from a given vertex might be bigger than 1. And that is true. And if that bothers you, then divide all of the 1s and the q's by like 5 or something. It's not going to make a difference to solving for the left eigenvector with eigenvalue 1. Okay. All right. So now an acyclic connected subgraph T is a spanning tree rooted at R if T includes every vertex of V and all edges of T point towards the root. So the picture on the right-hand side shows a spanning tree rooted at the vertex 1. So this is a tree, there's no cycles. It includes every vertex of my original graph, and all of the edges are directed towards the root. And the weight of a tree is going to be defined to be the product of all of the weights of the edges. So the weight of this tree here is q cubed. Okay, and now what does the Markov chain tree theorem say? So this is an old result, maybe from the 70s, due to Hill, and subsequently generalized by Leighton and Revest, studied by many, many people. It says that the stationary distribution is proportional to the measure that assigns to state tau the unnormalized probability, which is the sum of the weights of all spanning trees rooted at state tau. And so, for example, in this picture, in this example that we have here, if I want to compute the steady state probability of being at state 1, then what I should do, oh, sorry, there's a question.
Yeah, sorry, the definition of spanning tree. If I include the n from 4 to 2, which we already have there, then it's still be a spanning tree.
Oh, I want it to be acyclic as a graph.
Okay, so that's an undirected graph.
That's right. Yeah, thanks for asking. Oh, and maybe I should have repeated that for anybody in the Zoom audience. My spanning trees must be acyclic as undirected graphs. Okay. Okay, so now if I want to compute the steady state probability of being at state 1, then I should draw all of the spanning trees rooted at 1 and add up their weights. And so the weight of this tree is q cubed, but I think there's something like 5 other spanning trees rooted at 1. I have to write this all down and sum up their weights. And that will give me the unnormalized probability of being at state 1. T must be a spanning tree rooted at tau. I guess I didn't say here what is T. T should be a spanning tree rooted at tau. Does that answer your question?
The definition of a spanning tree, does it have to be a tree?
Well, it's acyclic. Yes, sorry, it should be a tree. It should be a tree.
So this is what Todd called arborescence, right? This is what appears in the directed matrix.
Yes. Thank you. Other questions? It's very closely related. I'm having a little trouble hearing you.
Saying that this is basically directed matrix.
Ah, okay. Yeah, that might very well be true. Yeah. Okay. What was that? Kirchhoff? Okay. All right. Any other questions or comments? All right. Okay, so all right. This is just a restatement of the Markov chain tree theorem. And it does, of course, give a positive combinatorial formula for the stationary distribution of any finite irreducible Markov chain. Now, however, if you play with this, you'll see that there's often a common factor in all of the unnormalized probabilities. And it can be very, very large, in fact. And moreover, if you get rid of that common factor, then you can have polynomials with negative coefficients. So let's look at this little example. So on our Markov chain on 5 states, if you use the Markov chain tree theorem, you will get these 5 polynomials as the unnormalized probabilities. But they all share a common factor of q plus 1. And if you divide by q plus 1, so as to get the sort of more compact or lowest terms on normalized probabilities, then you get this set of polynomials. And okay, there's a negative sign, so we don't like that so much. So all right, so this example motivates the following definitions. So let's consider an unnormalized measure on the set 1 through n, in which every component is a polynomial in some auxiliary parameters, q1 through qn. And again, like I'm not assuming that the sum of those components is 1, but we can always divide through by their sum if we want them to add up to 1. Now we'll say that psi 1 through psi n, this measure, is manifestly positive if the coefficients of psi sub I are positive for all I. And we say it's compact if there's no polynomial which divides all of the components. And so a sort of very general basic question is, consider a Markov chain whose transition probabilities are auxiliary parameters, q1 through qn. When should we expect such a Markov chain to have a compact, manifestly positive formula for the stationary distribution? So by the Markov chain tree theorem, there's always a manifestly positive formula for the stationary distribution. And of course, we can always divide by the greatest common divisor of all the components to get a compact formula. But when should we expect the stationary distribution to have a formula that's both compact and manifestly positive? So that's the first open question. To be what? It would be unique because you can take the just take the Markov chain tree theorem. It gives you a formula, a polynomial formula for every component, and then you just divide by the greatest common divisor. Other questions? Oh, sorry, I didn't repeat the question. The question was, should we expect it to be unique, that compact formula? Another question? Well, I think we have to be careful about what's the definition of generic. What I can say is I can produce like very, very, very large number of small Markov chains with a negative stationary distribution or non-positive compact stationary distribution. Yeah, I mean, just on 5 vertices, there's like hundreds. I don't want to put a different Q on every edge. Of course, if we put a different parameter on every edge, then we're fine. Yeah. So I definitely do not want to put a different Q on every edge. I just mean for all of them to be of that coming from that set Q1 through Qn and 1 as well. Yeah. I mean, perhaps there's no sort of completely general answer to this question, but maybe there are some nice sufficient conditions. Okay, now what if we apply the Markov chain tree theorem to the ASEP? Because I showed you the staircase tableau formula. Maybe it just comes directly from the Markov chain tree theorem. So anyway, so the Markov chain tree theorem gives a positive combinatorial formula for the stationary distribution of any finite irreducible Markov chain on n states, but in general, it has order of n to the n-2 terms, because that's the number of spanning trees. Now, in the case of the ASEP, I looked at that example, and it actually gives the staircase tableau formula multiplied by a polynomial in alpha, beta, and q, whose number of terms grows exponentially with n. So if you just look at a lattice of 2, 3, 4, 5, or 6 sites and look at what the Markov chain tree theorem gives you compared to what the staircase tableau formula gives you, the ratio in number of terms is just like incredible. Like for n equals 5, it's like more than 2 billion times as big. And for 6, I don't even know what that number is. Okay. Oh, any questions before I sort of shift gears a little bit? Okay. Oh, yeah. Sorry, Alex, I'm still having some trouble hearing. Oh, yeah, I don't know, but Sergey has something to say.
Not asked that question of two physics friends maybe 60 years ago or 70, and none of them was able to come up with a physics interpretation. In other words, like electric networks with some kind of diodes or something like that, where electrons can only go in one direction but not the other. In the symmetric case, there is such an interpretation. Yeah, because Laplacian has to be self-adjoint, basically, in physics.
Okay, thanks. All right, so I'm going to shift gears a little bit and just mention that there's connections to orthogonal polynomials. So there was this beautiful paper from 2005 of Uchiyama, Sasimoto, and Wadati, and they showed there's a close relation between the ASEP with open boundaries and Askey-Wilson polynomials. So Askey-Wilson polynomials are orthogonal polynomials in one variable x, defined using 5 auxiliary parameters a, b, c, d, and q, and they sit at the top of the hierarchy of the classical orthogonal polynomials. And so Uchiyama, Sasimoto, and Wadati, yeah, they proved that ASEP is intimately connected to Askey-Wilson polynomials. And then what was very useful to us was that we could combine their connection with our staircase tableau formula for the ASEP to find combinatorial formulas for the moments of Askey-Wilson polynomials. And so somehow having the connections between the probability model, the tableau, and the orthogonal polynomials was very useful in terms of allowing us to sort of import the combinatorics of the ASEP to describe combinatorics of these Askey-Wilson polynomials. Now there's actually a great number of variations of the ASEP which also admit beautiful combinatorial formulas and connections to special functions. So, so this is just a recap of what we've seen. We've got our open boundary ASEP, we've got staircase tableau, and then we have these combinatorial polynomials, which are these Askey-Wilson polynomials. And now something that Mark Heyman pointed out to me maybe 15 years ago was that Askey-Wilson polynomials are the one variable case of the multivariate Kornwinder polynomials. And so a natural question is, can we generalize this picture so as to replace Askey-Wilson polynomials by Kornwinder polynomials? What should be the upgraded version of the ASEP? What should be the upgraded version of the tableau? And so on. And the answer to that question, so we have sort of nice results in the two species case. So the upgraded version of the ASEP is going to be this open boundary multi-species ASEP, where now you allow another class of particles, which I'm drawing in gray. These are sort of second class particles which appear to black particles as holes and appear to holes as particles. And there's an appropriate version of staircase tableau as well, which we call rhombic staircase tableau. But now, because we have an additional class of particle, we need not just vertical and horizontal lines, but also diagonal lines. So somehow in the usual staircase tableau, the fact that we have two kinds of particles is somehow related to the fact that our tableau are comprised of boxes made out of two kinds of lines. And when we introduce another species of particles that's intermediate between the two, we have to introduce a sort of another line. And so these rhombic staircase tableau are now made of squares, but also rhombi. And I'm not going to tell you the definitions, but it's just to sort of give you the general framework that these are the upgraded versions of the probability model and the tableau that you need to connect to Kornwinter polynomials. So yeah, so we wrote a paper with this with Sylvie in May of 2015, and unbeknownst to us, Cantini was working on the same thing independently and wrote a paper within a few weeks, independently coming up with very similar results. And then together with Ole Mandelstam, we worked out the combinatorics of the two species ASEP and Kornwinter moments using these rhombic tableau. Okay, so again, I'm not giving you definitions here for Kornwinter or the rhombic staircase tableau, but just to show you this sort of trio of objects that's connected to each other. Now, by the way, Kornwinter polynomials are Macdonald polynomials attached to the non-reduced affine root system of type like affine C, sometimes called type affine, like non-reduced affine type BC. And so now another natural question is, can you modify this picture so as to replace Kornwinter polynomials by the usual type A Macdonald polynomials? And the answer is yes. But now we have to look at the multi-species ASEP on a ring. Oh, and by the way, if you sort of squint, then this lattice looks a little bit like the non-reduced affine root system of type affine C. And of course, this lattice here looks like the affine type A lattice. Okay, so now if we're interested in Macdonald polynomials, we have to look at this multi-species ASEP on a ring. And now we're going to allow particles that are labeled by non-negative integers. These non-negative integers are like their weights. And the hopping rate, the probability that two adjacent particles exchange will be either proportional to 1 or t, based on whether the heavier particle is clockwise or counterclockwise of the lighter. And there's, again, some nice combinatorics that allows you to understand the steady state distribution. There's something called multiline queues, first developed by Ferrari and Martin, and then by Martin. And one can also reformulate them in terms of tableau. And so these objects are connected to the usual type A Macdonald polynomials. And so the way this picture sort of came together was that in 2015, there was a paper of Cantini, De Geer, and Wheeler, which pointed out that if you look at the multi-species ASEP on a ring, and you look at its partition function, which is like the sum of the unnormalized steady state probabilities. If you look at that, the partition function, so this will be a polynomial in T, then it's equal to a Macdonald polynomial specialized at Q equals 1 and all the xi's equal to 1. And so they showed that some specialization of the Macdonald polynomial is giving you the partition function for multi-species ASEP. And at about the same time, a couple years later, James Martin was working on the combinatorics of the multi-species ASEP, and he'd found this multi-line Q formula for the steady state probabilities. Okay, so so far this story only had a parameter t in it. The multispecies ASEP only has a parameter t, and then of course his combinatorial formula for multispecies ASEP just involved looking at weights of multiline Qs, which were expressions in terms of t. But then what Sylvia and Oli and I decided to do was see if we could take Martin's formula, giving steady state probabilities for the ASEP, and upgrade it, add in xi's, add in q's, so as to give a formula for Macdonald polynomials. And so that was the content of this paper. You can introduce appropriate statistics on multiline q's so as to give a formula for Macdonald polynomials. And what's nice about this formula is that it's a little bit simpler than the formula of Haglund, Heyman, and Lohr, just in terms of number of terms. Oh, I think is there a question? All right. Okay. And then we shortly thereafter wrote a follow-up paper with Cortiel, Haglund, Mason, and Mandelstam, giving compact formulas for other versions of Macdonald polynomials, and in the process also introducing some quasi-symmetric Macdonald polynomials. Yeah, so I'm not going to tell you what quasi-symmetric Macdonald polynomials are, but the reason we knew they existed and were a natural object was exactly because of intuition coming from the multispecies ASEP and the combinatorics of these Qs. Okay, so I'm just trying to advertise the fact that if you have combinatorics connected to some model from probability, and you also know there's a relation to, say, special functions or orthogonal polynomials, questions coming from the probability model can lead you to ask questions that you didn't think to ask about the special functions, and can give you some new insights. Okay, all right, so now we've seen some variations of ASEP that are connected to Askey-Wilson polynomials, Horn-Winder polynomials, and Macdonald polynomials. What other special functions can we see? And well, the next class of special functions we can see is Schubert polynomials. So now I'm going to tweak the definition of the multispecies ASEP. We're still going to have particles hopping on a circle, and they will still have different weights. And in this picture here, I chose weights that were all distinct positive numbers from 1 through n, because that's what makes the connection to Schubert polynomials most explicit, but they don't have to be distinct. And this is a version of particles hopping on a ring that's called totally asymmetric, in that we only allow two particles to exchange places if the heavier one is clockwise of the lighter one. So that's something a little bit more restrictive than what we had in the multispecies ASEP. But on the other hand, our hopping parameters are a little bit more interesting in that we take into account the weight of both particles being exchanged. Okay, so this is called inhomogeneous multispecies TASEP. And it is again connected to combinatorics of multiline Qs, and also an interesting class of permutations called evil avoiding permutations. And this model is connected to Schubert and double Schubert polynomials. And just to give a teeny bit of history on this, back in 2012, Lam and I wrote a 4-page paper on this model, 4-page paper which only consists of conjectures and no theorems. And my shortest paper, my only paper, whose title ends with a question mark. And then in 2013, Arita and Malik gave they worked out the combinatorics of the inhomogeneous multispecies TASEP, showing essentially that the stationary distribution can be described in terms of multiline Qs. And then a few years later, Cantini wrote the first paper actually proving a connection to Schubert polynomials. So I'm not really going into any details here, but I'll just tell you that if you write down this Markov chain, so if you want to do a little experiment, let's say set all the y sub i's to be 0 for simplicity. You can put this model into your computer, ask it to solve for the stationary distribution, look at the unnormalized probabilities, and then for small n, what they're going to look like is products of Schubert polynomials times some monomial in the x's. And when n gets a little bit bigger, not all of the probabilities will look exactly like products of Schubert polynomials, but many of them will. And then in this paper with Donghyun Kim, we characterize the ones that look, whose steady state probabilities are products of Schubert polynomials. And they are the states corresponding to the evil avoiding permutations. Okay. Yeah, I'm not sure, but I don't know of a connection to Schubert for particles hopping on a line. That doesn't mean it doesn't exist. Yeah, so I don't know exactly how the ring comes into play here. It certainly makes life more difficult when you're trying to prove things, but yeah. Oh, a question in the chat. So, maybe I'll go here. Oh, except I don't know how to use this mouse. Okay, let me try to look on my computer. Oh, sorry? Okay. But as Macdonald polynomials also arise as eigenfunctions in the context of a Calligaro-Sutherland model of particles sitting on a circle. Oh, interesting. I don't know of a connection, but that would be really interesting. Yeah, I don't really know almost anything about the Calligaro-Sutherland model. Yeah, interesting question. Okay, any other questions? Okay. Okay, so now I just want to kind of recap the open problems that I have given so far, and also give a bunch of new ones. Okay, so the first open problem is, so recall that the stationary distribution of a Markov chain whose transition probabilities are some auxiliary parameters Q1 through Qn repeated. Certainly repeats are allowed and ones are allowed. When you write the stationary distribution in sort of lowest terms, it could consist of polynomials with negative coefficients. This was our example. And so question, when should we expect such a Markov chain to have a compact, manifestly positive formula for the stationary distribution? Okay. All right, that's the first open question. The second one is, so recall that there's n plus 1 factorial staircase tableau of size n, and they encode the stationary distribution of the open boundary ASEP. So a question I've been asked before, and I have asked before, what does a typical staircase tableau look like when n goes to infinity? Is there some kind of like limit shape or something? And the open boundary ASEP is interesting to people in statistical physics because it has boundary-induced phase transitions. So just to say a tiny bit about that, recall that we have particles hopping in at the left at rate alpha and particles hopping out at the right at rate beta. When alpha is very large and beta is very small, you have lots of particles coming in, and particles are sort of only exiting very slowly. And so you get this sort of high density regime. And similarly, if alpha is very small and beta is very large, you have very few particles in the system. So that's called low density. So those are two of the phases in the phase diagram. So anyway, so we could kind of ask other versions of this question. what does a typical staircase tableau look like when alpha is much bigger than beta, or when beta is much bigger than alpha?
Even a typical staircase tableau with a fixed top row or
Either one. Either one. Yeah. Yeah, I mean, I think first I was thinking not with a fixed top row, because then it will, for example, give you information about which state is most likely by looking at the top row. But we could also look within a fixed top row, what's the most likely? Yeah. Yeah, so if anybody is good at programming, I would be very curious to see what a sort of typical staircase tableau would look like. Okay. All right, next open problem. So there's a family of Macdonald polynomials associated to every affine root system. The usual Macdonald polynomials are those associated to affine type A, and they're related to multispecies ASEP on a ring, which looks like an affine type A diagram. The Kornwinder polynomials are the Macdonald polynomials associated to this non-reduced affine root system. They're related to the open boundary multispecies ASEP, which sort of looks like the Dinkin diagram for that root system. So what about Macdonald polynomials associated to some other affine root system? Are they related to the ASEP on some other lattice that maybe looks a bit like the Dinkin diagram? Okay, now I have a bunch of open problems related to the inhomogeneous multispecies TASEP, which is this model here. So we know that many steady state probabilities of the inhomogeneous multispecies TASEP are proportional to products of either Schubert polynomials if the y sub I equals 0, or double Schubert polynomials. And a conjecture from our 2012 paper is that in the case y sub I equal to 0, every steady state probability can be written as a positive sum of Schubert polynomials. And then a follow-up question is there some geometric interpretation for these probabilities? Another open question, when y sub I is 0, there's a multi-line Q formula for all the steady state probabilities. That's due to Arita and Malik. However, it's not known how to extend their formula in the case of general y sub I. And yeah, Donghyun and I looked at it a little bit, and it looked hard. Okay, so we've, oh, was there a question? Uh-huh.
So, one, I messed around a little bit with some of this data that you have, and it looked like everything in the sum tables was actually products of Schubert.
So that's true for n up to 4. For n equal to 5, I think you already see a few states where you have to get, where you have some sums.
So there were some, the sums that I saw would be expressed. At least some of the sums that I saw would be expressed.
Okay, so maybe we should, so I don't, so that doesn't agree with what I saw, but maybe, yeah, but maybe. So we have a table in our paper with Donghyun, and it's a table for n equals 5, and I think there's either 2 or 4 states where, oh, there's 4 states where we express the steady state probabilities in terms of sums of Schuberts. So if you have a way of expressing those as products, I would like to see. Okay, yeah, so all right, so far we've seen Askey-Wilson polynomials, Kornwinder polynomials, Macdonald polynomials, and Schubert polynomials, all related to variations of the ASEP. To give yet another example, there's some work in progress of Iyer, Mandelstam, and Martin relating the modified Macdonald polynomials, so these are the H's, to the multi-species totally asymmetric zero range process on a ring. And there's probably zillions of other examples that I'm not mentioning. Oh, so not that we're aware of, but Duncan and I had a very, very diligent referee, a really amazing referee, I have to say. It could have been one of you in the audience. We got this amazing referee report. It was 7 pages long, and it started out by saying, this paper is very well written. Here are some suggestions for changes. And it gave us like 99 suggestions for changes. But one of the things the referee was particularly asking us about was whether there was a relation to Grothendieck. And we could not find one, but that doesn't mean that it doesn't exist. Yeah. Yeah, after we made those 99 changes, the referee came back and thanked us and gave us another like 33 changes. It's like the most amazing like referee report ever. Series of reports. Okay, so very open-ended question. Choose your favorite family of special functions or orthogonal polynomials. Can they or their moments be realized as partition functions of a nice Markov chain? Okay, so that's all I have to say. Here's a picture of some of my co-authors. There's Olia and Sylvie, and here is Donghyun. And if you want to read more, I have a kind of a survey paper that just appeared this month, and explains some of the same ideas. And then I don't know. These are 2 of the most recent papers that we wrote on this subject. So thanks a lot.
Well, thank you, Lauren, for a wonderful talk. So we'll start with some questions in the room, and then we'll move to chat, which will be moderated by Joel. In the room.
So I went back to this years ago, and I forget. So but you have the formula for double polynomials and like staircase and all of that.
Oh, multiline cues, multiline cues.
Sorry, multiline cues. But you figure some kind of formula. Is there any hope of getting to the assured expansion?
Can you repeat it, Lauren?
Yeah. So the question was, since we have this combinatorial formula for multiline cues, can we get from that a Schur expansion? And yeah, we did look into that a little bit, and it was not clear, but it would be really, really interesting. Oh, could you speak a little bit louder? Oh, yeah. So, okay, I'll try to repeat the question. I couldn't catch every word, but I think you were asking about whether the probabilistic interpretation of the interior of the staircase tableau, not just the top row. Yeah, and that's a question that we've been sort of wondering about for a long time, coming up with an interpretation, probabilistic interpretation for the entries of the tableau that's not at the top. I mean, I guess I'd speculate maybe it has to do with the prehistory of where that tableau has been. And so so one of our proofs of this formula for steady state probabilities works by lifting the Markov chain of the ASEP to a Markov chain on the tableau themselves. And so I feel like maybe staring at that Markov chain would give insight to that question. But at the moment, I can't say anything in that direction. But I guess my speculation would be maybe it has to do with the history of where that tableau has been. Yeah. What was that? Oh, right. Yeah. I mean, in the high density phase, I would expect our tableaux to be like the top row would mostly look like alphas because there's lots of particles. I don't really know exactly what that will impose on the rest of the tableau though. What? Yeah, if it's like all alphas, then it has to be empty. Yeah.
Maybe we'll take like one more in the room and then we can see what's on the chat. Are there any on the chat, Joel? Okay, maybe one in the room and one on chat. Huh?
So you mentioned the ASEP case, your case tableau, and then this, or the feature, this something. There's sense where these statements associate something with a subset of the tableau.
Yeah, I was wondering about that.
Can you repeat it, Lauren?
Right. The question was, so there's two different formulas to get the stationary distribution of the ASEP, one in terms of staircase tableau, one in terms of trees. And the question was whether you could sort of, I don't know, pick out distinguished trees or I don't know, maybe I didn't quite get exactly the gist of the question. Do you want, or were you asking about how to prove the staircase tableau from the tree formula or how to look at? Right. Yeah. So the question was, what was, can you correspond every tableau to some large list of trees? Yeah. Yeah. A couple undergrads came to me at some point asking for an open problem to work on, and I asked them to look at this, and then they disappeared. And I think the question, I think it actually might be very hard to see what's going on just because the number of trees blows up exponentially. So in the smallest case, like the ratio of formulas is just by 4, I think, but you're going to quickly lose control. Oh, interesting. Yeah, maybe so. Yeah, that is true in terms of order of magnitude, permutations versus parking functions. Yeah. So maybe maybe it's not hopeless. Sorry, Alex, I'm still having trouble hearing you. Problem is I have a fan behind me.
Louder, Alex.
These are trees. So to get these trees, we have to look at the state diagram of the ASEP and then look at all of the spanning trees rooted at a given vertex. Yes. Oh yes. It's 2 to the n, 2 to the n minus 2. Yes. Yeah. Yeah. So it is. Yeah. Maybe it is hopeless.
Okay. Let's get the one chat question.
Trump, who asked, is there a connection between rhombic staircase tableau and random laws of Tyler? If there is, do you think that a question about the limit shape can be solved from the perspective of random Tyler?
Oh, that's interesting. Oh, should I repeat the question?
No, it's in the chat.
Oh, okay. All right. Okay. So I don't know the answer to that question, but a rhombic staircase tableau will be, it will be this kind of tiling together with this additional information of putting different weights in the tiles. So a priori, it seems like a much more complicated object, but yeah, I don't know, but it would be interesting if you could make a connection that way.
how it's brought by with such separations without notice?
Oh, I don't know if it can be described. So yeah, the question was whether the rhombic staircase tableau can be described in a local puzzle type way. So their definition is similar in flavor to that of staircase tableau. And entries are going to force a sort of empty path in some direction, but now your path is going to sort of like maybe zigzag northeast along your tableau. So I don't know of a way to relate them to puzzles.
Okay, so I think this has been great food for thought. Other questions, you can ask Lauren later, and let's thank her once again.